Hello, everyone. Welcome to the afternoon session of IDB 2026. And our first speaker will be Colin Sterckx, and he is going to talk to us and explain how to uplift non-maximal gauge supergravity.
Thank you.
Oh, you have.
Is this working? Everybody can hear me well? Perfect. So first of all, I would like to thank the organizer for inviting me to the nice city of Wrocław. It's the first time I'm doing one of these IDD conference. Okay, so let's dive in. The main point here is to tell you how do we uplift non-maximal gauge supergravities. This is based on some work that's not legible on the screen with David was a PhD student in Padova, and some work in progress for the end. So before I enter all the difficulties and so on, let me just start with some motivation. And the motivation is the following, is that these supergravities are great theory because we have supersymmetry and we can build a lot of solutions in those theories using that supersymmetry. In particular, we can find black hole solution, solitons, domain world. There are a lot of applications to ADS CFT. But those solutions are usually found in low dimensional gauge supergravities. And so it's very hard to directly give a string theory interpretation to those solutions. And what we want to do is to embed those solutions as a solution of type 2 AD or M theory in a kind of Zapline-like manner, so with like an internal manifold and then the external manifold that would be this low dimensional gauge supergravity in order to give some kind of string theory interpretation to those solutions. Sorry, and share the screen. Sorry. I hope I will have an extra minute at the end.
Can you say even more motivation?
Even more motivation. Yeah, that's basically it. You know, I don't think I need for this audience to motivate why you want to study black holes in terms of strings or whatever. Okay, but maybe what I can tell now is that the tool that we are going to use is that of consistent truncations. I don't think this is working anymore. I'm making you run and click once.
Can you try it again? Now it's perfect.
Perfect. Okay, consistent truncation. So I'm going to tell you in a bit what consistent truncation exactly means in this context. Before I lose you all after the lunch with all the details of the computation, I want to flash the main results that you should be taking home. So the main results here is going to be an algorithm for classifying embeddings of low dimensional gauge supergravity inside of type 2 and M theory. And this algorithm is based on generalized geometry and exceptional field theory. This algorithm is also going to give us some constraints on what the internal manifold has to be. And finally, depending on time, I'm going to tell you a bit about the various examples we can build. And I'm going to flash some uplift of a Dester solution inside of type 2V, which looks interesting for various reasons. Okay, so let's dive in. This is the plan. So I'm going to tell you about consistent truncations, what they are, how we will build them. Then I'm going to introduce the main actor of the game, which is generalized exceptional field theory, but we had a bit of generalized geometry already. So I hope you all remember that we all listen very well. And then I'm going to tell you what is how to uplift gauge supergravities, and I'm going to give you this example. Okay, so consistent truncations. First definition. So first of all, consistent truncation is first a truncation. So you start with whatever theory that you like. You have a bunch of fields, phi, and out of these fields, you're going to fix some of them to certain values, which is whatever ansatz that you choose, and you're going to remove those from the dynamics of the theory. You're only going to keep these phi 0 fields. And we say that such a truncation is consistent if the equations of motion of the reduced theories imply those of the full theory. So basically, the equations of motion of the reduced theory, just variation to phi 0, implies that the full equations of motion of the theory are valid. One thing which is not a consistent truncation, so I don't want to hear about it, is effective descriptions. So in effective description, what you do is that you keep modes which have a mass below some cutoff and you truncate them away. For example, Calabi-Yau compactification, you just keep the massless modes. This is not the kind of thing that we're going to do, because if you do this, you only solve approximately the equations of motion and you won't exact results. Okay, so what are good examples of consistent truncation? How do we build them? Well, the best way, the first way that we've learned how to build them, it dates back to Colin, and the idea is to start with some theory which has a symmetry group G, and then what you do is that you only keep the G singlets, everything which is invariant under this group G, and you will necessarily get a consistent subsector, because all the singlets in the equation of motion that we'll get at the end, they will never be able to tensor together and get product in order to produce something which is not a singlet. And so you are sure to have a good consistent truncation. The basic example is Karuza-Klein compactification. So you start with the Einstein action, and then you ask all the modes to be invariant under some translation in one of the directions. And what you get is a one-dimension lower gravity coupled now to a vector field, Karuza-Klein vector, it's off-diagonal term of the metric, and then a scalar. And one thing which is important is that this factor, 3, 3.5, and so on, you cannot change them. If you change them, you will not be able to uplift back to the full theory. So it's really sensitive to all of these small coefficients. A more involved example is this Sterckx fast reduction on a group manifold. So now instead of
Maybe I just didn't understand. On your first slide, you said that one application wasn't an example, but in the second one, you said it was. Could you say what was the difference between those two?
Yeah, so I was saying if you compactify on Calabi-Yau and you keep, so you can compactify on Calabi-Yau and do consistent junction, that's possible, that's one thing that you can do, but this is not what you do if you only keep the massless excitations. If you just keep the massless excitation, let's say you start to have the complex structure that varies through space-time. Once you uplift back to 10D, the issue that we're only going to solve the equation of motion up to whatever string scale or a Karuza-Klein scale and so on. In the case of normal Karuza-Klein, where you really take invariance along one direction, you are exactly solving the full equations of motion whenever you have a solution in the low dimensional supergravity. Okay, so on group manifold, you do the same thing. Internal space is now a Lie group. And what you do is that you take all the modes which are invariant under the right action of this G group. So this means that you're just expanding the metrics and all the P forms that you have in terms of right invariant one forms, which satisfy some properties. I'm claiming that this is giving you a good consistent truncation, which is Einstein gravity coupled to a gauge field with a gauge group G, and then some extra scalar fields. And now you should be a bit worried, because I was telling you, yeah, if I take products of singlets and so on, I cannot solve something which is not a singlet. But if I take the Einstein action, the Einstein action, I'm not just taking products of invariant modes when I look at the equations of motion. I'm also looking at the Levitshev connection acting on those invariant modes. And there you could worry that the derivative is going to solve something which is not a singlet, and that would break consistency. And the trick there to get to show the consistency in that specific case, and that's the same kind of trick that we're going to use in a more general setting, is to split the Levitshev connection into one piece which is called compatible. So it's a torsionful connection that is going to vanish when it acts on any of those right invariant one forms, or the equivalent killing vectors. And then an extra piece which is just the torsion, because Levitshev is only torsionless connection, so you have an extra piece which is torsion. And if this torsion is itself a singlet, a G singlet, you can always write something like that. The Levitshev connection acting on the right invariant forms is just giving you some, here is the structure constant of this group G, the Lie algebra of the group, and then tensor it with the right invariant forms. And so you're once again only producing invariant object, and you are sure that the equations of motion, the truncation is consistent. Sorry. Okay, so these were like basic examples, and we are going to try to do this one with Einstein action, with supergravity. But one more thing I would like to know about consistent truncation in general is the fact that they are not unique. So I was telling about the fact that we want to classify uplift and so on. So what do I mean by this? So I had this example that I really like, which is you start with M theory, and then you compactify it on 2-3 spheres over an interval. That's just a 7th sphere. And Luch, Letitia, both have shown that this truncates consistently to an SO4 gauge supergravity. You can do something else. You can start with type 2B supergravity. You can now compactify on 2 S2s over a Riemann surface. If you choose everything well, that's S5 times S1 over ATS4. And then you can once again compactify to the same gauge supergravity. So a given gauge supergravity can have multiple uplifts. Okay? It doesn't mean that those two theories are dual in some sense. It just means that they have a common subsector. There is a subsector which shares the same equations of motion. Okay, so what are the open questions that we want to answer here? So the first type of open question about consistent function you could ask is more of a top-down question. You start with some solutions, maybe yes, some costly solution in type 2B in M theory, and then you could ask, okay, around that solution, can I build a consistent truncation keeping some of the modes in order, for example, to deform that solution for the black hole to do whatever? And the answer is that if you have supersymmetry, and you are starting with a Minkowski or ADS background, you can always do a consistent truncation down to the pure unextended supergravity with the gauge group, which is specified by supersymmetry in D dimension. But whenever you don't have supersymmetry, so for example, if you want to do consistent truncation around the Sitter vacuum, or if you are requiring the existence of extra maximal multiplet, that's what I mean by pure. There is no extra maximal multiplet, just the Einstein. The metric supermultiplet, then it's an open question. Nobody knows how to do this. There's the other side of that coin, which is a bottom-up question: is given a gauge supergravity in D dimension, how do I uplift it? And for maximal gauge supergravity, so with the maximal amount of supersymmetry, this was solved by Inverso and Provere, which are written there. But for non-maximal supergravity, so far it was an open question, and this is what we are going to try to do. And it's super interesting to have like a non-maximal gauge supergravity, because in maximal gauge supergravity, you have a bunch of fields, the booster motion are very complicated, and so having simple model in order to build a new solution is very important. Okay, so how do we do this? To show you how we do this, I need to introduce a bit of generalized geometry and exceptional field theory. So far we've seen just before the n=1 version of generalized geometry. I'm going to show you a bit more like the n=2 version of generalized geometry, which are based on this exceptional Lie group. So what is exceptional field theory? You should think of it as just a dictionary between whatever type 2 and or M theory and another theory in which you've separated somehow an external piece, external manifold times an internal manifold, and you've taken all the metric, the T-forms and so on, and you've rearranged them in a way that's manifestly invariant under this exceptional Lie group, which are the U duality groups of string theory. So I'm going back to dualities, so I can be here. Okay, so what is this exceptional field theory? What is generalized geometry? The trick to show easily these symmetries under this exceptional Lie group is to add, it's a bit of a trick, but we add some internal coordinates. So I start with some internal manifold with the internal small y, and I'm just going to add a bunch more big Y till I fill out a representation of EDD. Okay, that's a weird thing to do, but if you do this and you look at vectors on now this extended space, and you look back how this generalized vector representation R1 splits under the GLT group that's acting on this Ym, you realize that you have always a vector piece and then a series of even or odd T-folds. And those correspond precisely to the diffeomorphism that you have in Einstein theory, the generator of the diffeomorphism, and then the generator of the gauge transformations. Then you want to build an algebra out of these generators of putative gauge symmetry, and this is the generalized Lie derivative, which is nothing more than the normal Lie derivative plus some extra correction for everything to close nicely. The only problem somehow is this definition of the Lie derivative, but that's not a bug, it's a feature, is the fact that it doesn't close unless everything is independent on all the extra coordinates that you had to add. It can only depend on the small y coordinate. So you are back to where you started and everything is nice, but now you've gained this EDD invariance in your equation. Then you need to add some field content, a generalized metric, generalized Kaluza-Klein vector, p-fonts, and so on. And since I'm going to talk a lot about geometry in a moment, about G-structure and so on, I just want to make a small parallel between normal geometry, the one that you are used to, the standard differential geometry, and generalized geometry. So in normal geometry, at each point on the tangent space, you have a GLD group acting. Now this group is going to be EDD. So every time you think about GLD, you specify EDD. Every time you think about a vector field, you think about a generalized vector, and that generalized vector comes with a set of section constraints, and these section constraints are encoded in this matrix epsilon, and those are just telling you which are the coordinates which really act, which really correspond to the small y coordinates, and which one are just like extra coordinates that you added for convenience. And then field content is the same thing. You started with a Willbein for gravity. Now you have a generalized frame, which instead of being in GLD over SOD, is in EDD modeled by its maximally compact sub. Okay, so what did we gain by doing this whole thing? What we gain is that now we have a very large symmetry group on this right-hand side. And so I can look at new GS invariant subsector in a specific way to build new consistent truncation to low dimensional gauge supergravity. So I'm doing this because now I have a larger group and I can do truncation with respect to larger GS group or more different GS group, which are not necessarily inside of GS. And now there is this statement that I'm going to unpack slowly. But if you want to build a consistent truncation in exceptional field theory, what you need to build is a generalized GS structure with constant and GS invariant intrinsic portion. So what is a GS structure? Basically, it's a fancy way of saying I can take GS singlets, that's just that, or I can have a basis of GS invariant objects, which are well defined. And this GS invariant intrinsic portion is the same thing as in the Schacht-Barth ansatz. It's just saying that I have this constant structure, constant, for my D group, and I can expand this Levi-Civita connection in terms of objects which are not going to break consistency. Okay, so now the question how to apply gravity is just reduced to classify GS structure with constant GS invariant intrinsic portion. And as we're going to see, this intrinsic portion is basically going to give us what the gauge group of the lower dimensional gauge gravity is. So you fix some gauge group, you fix some intrinsic portion, and then you want to classify this object GS structure with GS invariant intrinsic portion. Okay, so I said GS structure, they are a fancy way of talking about invariant objects. What does it precisely mean? So there are two ways of thinking about it. The first one is in terms of section, the other one is in terms of frame. So in terms of section, a GS structure is a series of sections of the generalized tangent bundle. Ka is just like A is just the number of invariant sections, M is the index in the generalized tangent bundle, such that at every point, these sections are stabilized exactly by the group GS or a group isomorphic to GS inside of E7. And then what is the torsion for a GS structure defined by this object? It's super easy to compute. You just take generalized V derivative of one section with respect to the other. And whenever you can expand this left-hand side inside of, as a linear combination of the section themselves, and that those coefficients are constant, you have a constant GS singlet, and you have a constant GS singlet intrinsic portion, and so you have a consistent truncation. So from the point of view of section, the name of the game is to build GS invariant section and to check that those close nicely under the generalized V derivative. And as I said, this thing, you should think of them as the structure constant of the gauge group of the low dimensional gauge gravity. Okay, now there's another way of thinking about this, which is in terms of frames. So like normal geometry, you have the Willbein, that's the element of GLD over SOD, and that defines actually for you an SOD structure. The same thing happens in generalized geometry. A GS structure is just a globally well-defined section of EDD modeled by GS. And that is fairly easy to build because I can just check when I change maps when I change charts, sorry, that's the difference between my different frames are just living inside of this GS. Whereas in this left-hand side, it's harder to do because I need to check that this stabilizer is isomorphic to GS, but I don't know exactly what's the identification. In the right-hand side, I know precisely what GS group I have chosen, so it's very easy to build those frames. What's harder to do is to compute the intrinsic torsion of those frames because you need to build a compatible connection, so a connection such as it's a generalized connection, but really think of it as usual connection, such that the frames are covariantly constant. And then I need to check what the intrinsic torsion of that compatible connection is, and then I must check that it is a constant GS singlet. So this is very hard to do. And what we're going to do is that we're going to use both of those formulations to simplify our life. So I'm going to use this one to check that I have a GS structure, and I'm going to use this one to check that I have a constant GS singlet torsion. And then if both of those things define the same GS structure, they're related by this equality, where this P is just a projector onto the GS singlets, which are then giving me the sections. Okay. Questions so far?
I'm a little bit confused by your statement about having this constant XABCs, because usually this is a statement about parallelizable spaces. And so parallelizable spaces have a trivial structure group.
Yes.
So how can you achieve this intuition? In general, you cannot achieve it globally for non-progressive structure group, right?
So what's happened here is that it's A, B, C indices. They do not go from 1 to
So you don't have the full frame. You just have a set of vectors, of generalized vectors.
You know, I don't have a section of EDD modeled by the identity. I have a section modeled by GS.
Okay.
So
Then it makes sense. Thank you.
Thanks for the question. Okay. So how do we go from this to how do we solve all of these constraints? What you do is that you start by solving this torsion constraint. So you assume that you have those sections, and then you go through the motion. So I want to solve that equation, and to do this, I first look just at the vector component of that equation. So those are like big generalized vector. I just look at the vector piece of it, and if I do this, all my equations simplify. So I just look at the vector component inside of the generalized vector, and I realize that the generalized Lie derivative is just the usual Lie derivative of vectors. And so that just tells me that the internal manifold must admit an action of the gauge group of the low dimensional gauge supergravity I'm looking for. And then if you look at it, the only thing that you can write is a coset space fibered over whatever extra number of dimension that you need for the right number of dimension to uplift in type 2 or M theory. This group H still has to be specified. There can be like multiple solutions then.
Yeah. Although at this point, so it's a little bit more complicated here, an exception of your theory, right? Because the x's are not antisymmetric with respect to the first two indices. So you need more information than just the gauge group, right? But also a representation of the gauge group to find the full axis.
So what I'm doing here is that this X is the embedding tensor of the low dimensional gauge. Right? I didn't want it to go like into the detail of embedding tensor formalism, but this is completely fixed by which gauge supergravity I want to fix. And so I agree, some of those things are going to be zero.
Theory data is not sufficient, right? So because we had actually, so that's why I asked, because we had a paper where we were constructing this explicitly, and there you see the information about the group is not sufficient to fix that. So you also need a representation.
There is, yeah, but this representation thing is built from the fact that the vector they live in the GS singlets of the whatever representation of EDD, and that gives you like a unique representation inside of EDD by specifying the GS, and GS itself is specified by what is the field content of the low dimensional gauge.
Yeah, sorry, I don't want to.
No. But let's discuss this afterwards. And as you're going to see, I'm going to make an extra assumption, which I think you are going to enjoy. I'm now going to take the gauge group to be compact, and then everything simplifies a little bit. So it turns out that if I'm not going to go into the details, but if you assume some sort of topological condition, if you assume the gauge group to be compact, there's always a choice of gauge such that actually the full generalized vector are are built out of co-closed equivalent P form. And so this, if you build like this co-closed equivalent P form, you have the more generic vectors that are going to solve this torsion condition. Now you still need to impose the stabilizer of the section closed under GS, and for that we're going to move to the frame picture. So the fact that we can show that the sections themselves are equivariant, it's possible to show that the frame must also be equivalent under this gauge group. And then there's only one thing that we can do. It's writing it in this way. So on the left-hand side, you have a coset representative of this coset space GG over H. On the right-hand side, you have the round line that's built from the Morat-Cartan forms. And then in the middle, we have what we call the flat frame, which can only depend on the coordinate on this extra basis, on this extra manifold. Okay, now you still have constraint on this. You cannot build anything because you need this frame to be connected to the sections that we have built. So you need that when you project the frame on the left-hand side on the singlet and on the right-hand side on the vector index, you get the killing vector acting on GG, and you can show that this boils down to an equation, an algebraic equation between this element of EDD and the embedding tensor of the lower dimensional gauge supergravity you're trying to uplift. This also is going to fix H, and there's actually only one type of H group for any type of uplift, either in type 2 or M theory. So this is telling us which type of internal manifold we can have.
Oh, I have over 10.
And note that?
No, you have over 10 minutes.
Okay. Okay, so this is like the final, summary. You need to solve one algebraic constraint, which is specified here by the gauge group of the low dimensional gauge supergravity. P is given by the field content of the low dimensional gauge supergravity. This epsilon is just the section constraint. And then you just need to solve an extra partial differential equation, which is that the sections are built out of closed P form. And so you're just asking the X derivative to vanish for each of the P form components of the sections. And it turns out that this is a partial differential equation just on B. You've completely factorized out this gauge group over H coset space. Okay, so this is like the main thing. An application maybe. So the application I want to show you is once again this half maximal 4D supergravity with an SO4 gauge group. It turns out that there are 3 different ways of gauging SO4 inside of that gauge supergravity. There is one type of gauging in which there is an ADS4 n equal to 4 vacuum. There is one type of gauging which has a de Sitter vacuum. This is related to this de Raux-Weidemann angle. And it can be obtained from the ADS gauging by doing an orientation reversal on one of the 2 SO3 factors inside of SO4. There is actually kind of group theory behind it. And then this is the last gauging, which is just this Friedman-Schwarz gauging, in which the star potential is just a runaway potential. And we're going to focus on the uplift of those 2 first gauges. Okay. So if you try to do like this for the ADS gauging, the structure group is fixed to be SU4. Why SU4? It's because so the exceptional theory for compact fiction to 4D, the exceptional group is E77, and the maximally compact subgroup is SU8, which is the R symmetry acting on the various gravitini that you have, the 8 gravitini that you will have. And then SU4 is actually removing 4 of those gravitini which are not invariant. So that is 4 gravitini, and so you have an n equal to 4 theory. The gauge group is 2 copies of SO3, that's why SO4. And then trying to solve this algebraic constraint, you realize there's only one thing that you can choose, is choosing this H to be U1 times 1, and you get the internal manifold to be a couple of S2s 5 over a Riemann surface. Now you still need to solve the partial differential equation, which is just a PDE on sigma, and you realize that any solution for this PDE can be expressed in terms of 2 harmonic functions or 2 holomorphic function. And whenever you choose any of this H1 or H2, you get a different consistent truncation or different uplift of this 4D gravity type 2D. And this is not to frighten you, although like you cannot see very well, but what I wanted to show here is that this is the generalized section that we have, and they're always built as a killing vector acting on these S2s, and then there are a bunch of closed and equivalent forms which are expressed in terms of this H1 and H2 every time. So this is like basically the solution to the uplift. So what do these uplift corresponds to? Once you have looked at the section, you can look at the generalized frame, and from the generalized frame, you can build the various fields of type 2B, which are what they are. But this is like, for example, just the uplift of the scalar sector. The full uplift is in the paper if you're interested, or downstream. It depends on the various scalars of the 4D theory. And if you look at the ADS vacuum of the 4D theory and you uplift, you realize that they correspond to these families of solution built by Dr. Estes and Pelle, which has this half maximal solution in type 2B with an ADS4 factor. And those correspond in turn from the ADS-CFT correspondence to the Gaiotto-Witten brain setup. So what's interesting now is that if you want to build a black hole inside of this, if you want to put like some temperature, you can do it. Like you have the ansatz, you just plug whatever solution you have in 4D and you uplift. If you want to look at either domain rules or so on, you can do it, you just plug in the solutions. What about the De Sitter one? So this was like not work in progress, but this is now, we are in the domain of work in progress. So this orientation reversal of the second SO3 factor that allows us to go from anti-De Sitter to De Sitter, it can be implemented as a group element inside of E7. And so we will have the same algebraic ansatz with the same flat frame, but different PDEs to solve. There will be a bunch of minus signs that are going to pop here and there. You can still solve the PDE. It turns out that they also depend only on two harmonic functions, H1 and H2. And I don't have the full uplift to present to you today, but what I can tell you is that if you choose like two harmonic functions, so eta and alpha coordinates on this Riemann surface, we are fibering the two spheres over. You do some change of coordinates, and now you get a metric which has like some warping factor, a De Sitter 4 factor. Those are the two S2 factors, and then there's the metric on this Riemann surface. There is the dilaton, which is turned on and which is linear in this eta direction. You have the 2-2 form, which are turned on and which are also like linear or proportional to e to the eta or e to the minus eta. And everything else is completely independent of this eta direction. So what can you do now? And this is fun, I hope, is that you can actually take this full real line that was, parameterized by its eta coordinates, and you can quotient it, so you can make this eta periodic of period t. If on top of that you do an S folding, so whenever you go along the loop, you act with an SL2 element, SL2R in this case, and then you have a good symmetry for the theory and for the solution. And now what you have actually, you have a compact De Sitter solution. So that goes against this no-go theorem from Maltasena and Newtonians. Because now we can compute that, for example, the Newton constant is non-zero, but is proportional to this to the period of this eta circle. So it evades that theorem just by doing this S folding, right? If you still have the infinite length of eta, you will have a zero effective Newton constant. You have a finite internal volume, and this R coordinate is actually of finite length. As you move along this R coordinate, you reach the end after a while. Only bad thing about that solution is that the curvature diverges at the two extremities of this R thing. So you would expect to have some alpha prime correction playing some role there, but you would not expect to have a GS correction. One of the things that you should check is whether or not the solution is stable. We guess it's not stable, but who knows? We could be lucky. Okay, so let me maybe conclude with some.
Wait, one question. So with this S folds and T folds, usually also the problem is that you cannot really get a very small cosmological constant. Is this here the same? So can you get small cosmological?
So in this case, so it's you don't have scale separation. Okay. What you mean? So the size of the internal space is of the order of the size of the external. I mean the De Sitter radius.
Okay, so but it is the very large radius, right? So I mean, it's a weakly curve.
Yeah. Yeah, everything I do is classical, so there is like I'm avoiding highly curved. Okay. So let me maybe conclude with some outlook and future direction. So since we've done this uplift for n equal to 4 gravity inside of type 2b, it would be very interesting to do the same kind of classification for uplift inside of M theory. Those are a bit harder because this algebraic condition becomes a lot scarier, but it could be done in principle. It would also be interesting to look at the uplift of this Friedman-Schwarz gauging, because we have this runaway potential, so that could signal either some kind of decompactification or some kind of brain that is sitting somewhere in the internal space. And then you can go down, and you can go to other number of supersymmetry, other number of dimensions, and so on. So far, the method that we've built, it doesn't work for massive 2A either, so that should be refined. And it doesn't really work for non-compact gauge groups, so it gives us some simplifications, but it doesn't give us everything. So it would be very good to have a generalization to the effect of non-compact gauge group in non-maximal gauge gravity. And then, of course, I would be super interested into learning if there are other types of de Sitter fold, maybe in different number of dimensions, maybe without this curvature blowing up, or studying the stabilities of those solutions, and so on, or just choosing different functions, H1 and H2. Those were an example just to test the uplift, but maybe we could build other types of uplifts using the same method. And on this, I thank you.
Fine, thank you, Bill. Any further questions?
Sorry, yeah. If I may, Alex? Oh, maybe not.
Yeah.
Okay, let's go with the Zoom question.
You asked to speak.
Can you speak up? On Zoom?
Oh, me?
Yes.
I can speak up, but I think the volume control is at your end.
This is good. We can hear you.
Okay, so my question was, thanks for the talk. So you're looking at these S-fold uplifts. Is this because you're particularly interested in S-folds per se, or is it because that's the only way you have to evade some no-go or something?
Yeah, so in this case, the S-folding was just a method to avoid the no-go. In theory, I don't really need the S-folding just to do the uplift, because all of these uplifting procedures are always local statements about the equations of motion, which are local. They're not telling us anything about the global structure. And so I can choose to put this S-folding to avoid the no-go, but the solution would still stand without the S-folding. I don't know if this answers your question.
Yeah, sort of. And so, but does this technique afford you any insight into stability, perturbative or otherwise, of such solutions?
So within the modes of the n equal to 4 theory, we say that the solution is stable, but we cannot say anything about the other modes which are not capturing the 4D n equal to 4 theory. One avenue of research that could be interesting if you are worried about stability would be to try to generalize these methods of Kaluza-Klein spectrometry to non-maximal consistent truncation. So those are methods based on exceptional field theory that allows the full Kaluza-Klein spectrum of a given solution, but they require a consistent truncation for maximal gauge supergravity. And so it would need to be refined if you want to think about solution that comes from a non-maximal gauge supergravity.
Great, thanks.
Thank you.
All right.
Yeah. So in 4 dimensions, the uplift of maximal gauge supergravity, let's say it has E7 symmetry. The uplift to 11 dimensions has a hidden E11 symmetry, right? That's what the next talk is roughly going to be about. In this context, for the non-maximally gauged supergravities, are you saying there's some symmetry that explains it in 11 dimensions or 10 dimensions in the same way the 11 would, or is there some generalized geometry structure that explains why, or, why you can go up and down between them?
Yeah, that's the whole point of the generalized G structures.
So how would you say it simply, if that makes sense? Like in the same way, I can say E7 is contained in E11, you can see that in the picture. From this perspective, I don't see the simple way to say it, if that makes sense. There probably is one, I just don't see it.
Yeah, so what happens is that if you look, let's say E7 model, for example, if you look at what are the representation of the gauge parameter, they fill out precisely a representation the 56 of E7.
Right.
Okay, and if you look at how do the field transform under that, they transform exactly as an element of E7 modeled by SUA. It's just like really you take you take the thinking diagram of E7, right? You choose an SL7 subgroup and then you split everything and you see the whole structure appearing.
And the same thing happens in 11. You have E11 mod some subgroup and you get supergravities.
I don't want to say anything about E11 because this
Yeah,
is beyond my paycheck.
Yeah.
But yeah.
Okay, great. Wait, sorry, so the bullet point summary is what are you quotienting?
I'm looking at some GS invariant subsector where GS is a subgroup of E7. In the same way that you would take a U1 invariant subsector inside of GLD to get times that high.
And for in 10 dimensions, is there a similar quotient? Is there even a group structure involved in the uplift? When you uplift, are you uplifting the E7 modeling to a bigger group, or have you looked at groups?
I stopped there. I mean, I have external
You stopped
space.
there.
So at E7 modeled by.
Okay, I'm just saying that the uplift, there may be a group structure in the uplift as well. On the group side, there may be something interesting.
Okay, let's discuss.
All right, lovely. Please let's thank our speaker again.